Physics from Chapter 11, numbers 52, 56, 60, and 66. Number 52. Cockroach of mass m lies on the rim of a uniform disk of mass 4m. Here's the cockroach on the rim. And the whole assembly of disk plus cockroach is rotating with an angular velocity of 0.260 radians per second. Then the cockroach walks halfway to the center of the disk. What's the angular velocity now? Well, the angular momentum is conserved, so that means the rotational inertia, which is of the disk 1/2 m r, they didn't tell us the r, did they? R squared, which I times omega 0.260 is equal to I, which, oh dear, I forgot to add the cockroach. So that's plus the mr squared of the cockroach. Sorry about that. Sorry, cockroach. Forget you. How could I? And then now, afterwards, we have 1/2 mr squared. The disk is the same, but now cockroach is at m times 1/2 r squared. Make sure you square that whole thing. Times the final angular velocity. Okay, so let's see what we have here. This is half of 4 is 2, so 2 mr squared plus mr squared, that's 3 mr squared times 0.260 is equal to, and here we've got 2 mr squared plus 1/4 of an mr squared, 2.25 mr squared times the final angular velocity. So it will increase, we know that, and it will increase by a factor of 3 over 2.25 times the original 0.347. We want to know how much did the kinetic energy increase. So the original kinetic energy, actually let's do the new first because they went new over old, right? So the k over k sub 0 is equal to k as 1/2 I, which was 2.25 mr squared, did that already, right, times omega squared over 1/2 I, did that already, right here, times the original 0.26 squared. So the halves cancel and the mr squareds cancel. I get 2.25 over 3 times 0.347 squared over 0.26 squared. So about 1.336, 1.34, something like that. That ratio is 1.34. So the kinetic energy increased by 34%. That's one way of looking at that. Where the heck did it come from? Well, in this kind of situation where we have the changing rotational inertia and it's changing internal to the system, something has to do work on the system. So cockroach does positive work on the system. Right? That's number 52. Number 56. Let's see what we have. This is the long jumper. So this is really just a matter of figuring out what the angular momentum of the arms are through the common rotational axis. So we basically have two rods about their ends. So the rotational inertia of each one of those rods is, a rod about its end is 1/3 ml squared. And I have two of them, and I know that the angular velocity is, they didn't actually give me, let's see. Oh, sorry, I'm looking at the wrong one there. They didn't give it to me. They gave it to me in revolutions per second. So they tell me that the angular velocity is 1 revolution in 0.7 seconds. 1 revolution is the same as 2 pi radians in 0.7 seconds. So that's 2 pi divided by 0.7. That's about 8.98 radians per second. So if I wanted to find the total angular momentum of the arms, assuming that they're rotating in the same direction, which is not really clear in the problem, but I'm going to assume that they are rotating the same direction, that would be the most effective way of doing this. So, oh, and wait a minute. Sorry. One of them does this in... One of them does this and the other one only does half a revolution. So sorry, I gotta find that too. So that's gonna be half of this. So what, 4.9? No, that's not right. 4.49 radians per second. That's one arm, that's the other. Sorry, I forgot they were different. So we want to find the total angular momentum. So we have angular momentum of the first arm plus the angular momentum of the second arm. So that's I, 1/3. Mass of each arm is 4 kilograms. The length, 0.6 squared. That's going to be the same for both arms, so I'm going to factor that out and then just add together their angular velocities. So 8.98 plus 4.49. And that's it. Two rods about their ends. Kind of a gory way of describing a human being's arms, but 4 times 0.6 squared times 8.98 plus 4.49. So 6.47 kilogram meters squared per second. That's the total angular momentum of the two arms. Number 60, we have got a kind of a ballistics pendulum situation here, but this time it's got more physical stuff going on. We've got a rod and a block, and here comes the bullet toward the block. So let's see, bullet has a mass of 1 gram, and the block has a mass of 0.50 kilograms. It's attached to the end of a 0.60 meter rod, so that's from here to here, 0.60 meters of a mass half a kilogram. The block rod bullet system then rotates in the plane of the figure about a fixed axis at A. The rotational inertia of the rod alone about the axis is 0.060 kilogram meters squared. And just treat the block as a particle. What then is the rotational inertia of the block rod bullet system about point A if the angular speed of the system... Oh, sorry, that's the end of part A. So let's do that. What then is the rotational inertia of the block rod bullet system about point A? So the block rod bullet system about point A, the rotational inertia of the whole thing is just rod plus block plus bullet. Do they tell me the velocity of the bullet? I feel like I need to know that. Oh, I guess I don't need to know that until I need to do the momentum. Sorry, I guess I need to know that later, or find it later. Okay, so the rod, I think they told us, right? The rod alone is 0.06. The block they said to treat as a particle, so that's the mass of the block, 0.5, and that's our m, r squared. If we're treating it like a particle, then it's 0.60 meters from the axis. So that's mr squared for that particle. And then there's also a bullet now stuck in it, which has a mass of 0.001 at that same radius. So notice that this makes a very small difference in the rotational inertia. Just like if we were adding masses, adding 1 gram would make a very small difference. So I don't think I'm going to even bother with that because I wouldn't keep it in my sig fig. So 0.06 plus 0.5 times 0.6 squared, 0.24. And if you want to just see what it would look like if you added this, plus 0.001 times times 0.6 squared. So I wouldn't keep those sig figs anyway, right? Even if I kept 3, it'd be 0.240. So sorry, bullet, it just doesn't matter. So that's part A. B, if the angular speed of the system about A just after impact is 4.5 radians per second, then what is the bullet's speed just before impact? So I have angular momentum before is equal to angular momentum after. The angular momentum before is just the angular momentum of the bullet relative to that point, and the angular momentum after is the angular momentum of the rod, block, bullet system, all those things stuck together. So let's see, this is an RMV sine theta, and this is an I omega. So let's see what we know. We know the R for the bullet is 0.6, the M for the bullet is 0.001, the V for the bullet is what I'm looking for, and the sine of theta, those are perpendicular, so it's 1. The I total is right here, 0.24, and the omega they told us is 4.5. So, solving for V, 0.24 times 4.5 divided by 0.6 and also divided by 0.001. 1,800 meters per second. That's fast, but it is a bullet after all. Oops, sorry, you couldn't see that last bit, could you? There it is. And last, certainly not least, is this problem about the block, little green block. That's what they call it in Russia, little green block. And I'm going to hit this rod, and it's going to stick to it, and they're going to rotate. I don't know how far, but I would like to know what angle. Right? So the considerations here are we need to go from here. How fast will the block be going? That's an energy problem. And then they'll stick together. That's a collision, a conservation of angular momentum problem. And then how high will it go? That's an energy problem again. So let's see if we can make our way through all of that. And make sure, I think my little iPad contraption is sagging a little bit. Maybe it's okay. Hope it doesn't fall down. Okay, so first we're going to figure out how fast the block is going. Right now it is at a height, sorry, I should write this, so the mgh is going to turn into 1/2 mv squared, and the v of the block will be the square root of 2gh. And that's the square root of 2 times 9.8 times the h is it 0.2, I believe? And that is square root of 2 times 9.8 times 0.2 is 1.98 meters per second. That's the velocity of the block. Now it's going to collide with the rod. So this is a conservation of angular momentum problem. We have the small l of the block and then the big L of the block rod system. This is an RMV. This is an I omega. The sine theta here, it's going to crash in perpendicular there. So the sine of theta will just be 1, sine of 90 degrees. So R is 0.4. That's the R, that's how far the block is when it collides here away from the axis, 0.4. The mass of the block is, was it 0.5? No, 0.05, sorry. The velocity of the block is 1.98. On this side, the total rotational inertia is the rotational inertia of the rod about its end. That's a 1/3 m L squared. That's a rod about its end. Plus, I'm just checking my numbers there, make sure everything's right. Yeah, I think that's all right. Plus the mr squared of the block, m r, oops, the block is also at a full distance of 0.4 from the axis. So 1/2, it's not 1/2 either, is it? It's 1/3. I think I said that. 1/3 ml squared for the rod plus mr squared for the block, which we are treating as a particle, times angular velocity. All right, and that's the angular velocity after the collision, angular velocity of the block rod system. Let's see if we can crank that out. So 0.4 times 0.05 times 1.98 divided by 1/3 times 0.1 times 0.4 squared plus 0.05 times 0.4 squared. I think that's it. That's 2.97. radians per second. Okay, so that's the angular velocity of the rod with the block stuck to it after the collision. So how much energy does it have? Well, it has rotational kinetic energy that is going to transform back into gravitational potential energy. So rotational kinetic energy, 1/2 I omega squared, is going to turn into mg, and then the change in height of the center of mass, mgh, but I just want to be specific here that we know, to make sure we know what we're getting ourselves into here, what we were finding. So that's 1/2 times the I is that whole thing. I'm just going to write I here, right? That's that, times omega, 2.97 squared is equal to m is 0.15, that's the mass of the whole thing, g times the change in height of the center of mass. And I believe I'm going to save you the trouble here. I'll remember, because we did this in class, that the delta H of the center of mass comes out to be 0.040 meters. Okay, that is the change in height of the center of mass. But where is the center of mass of this thing? Well, it's not the center anymore because it's got a block stuck to the bottom of it. So I've got the rod and then this extra block stuck here. The center of mass would have been here. So the center of mass of the rod can be treated like it's here. So the rod is here and has a mass of 0.1. And the block is here and has a mass of 0.05 kilograms. So you have to remember how to do the center of mass calculation here. I'm going to call it the y-coordinate of the center of mass. It's 1 over the total mass. And then in here I have to multiply mass times location plus mass times location for all the pieces. I only have 2 pieces. This one is uniformly distributed, so we treat it like it's all the masses located at the center plus this particle. Since I'm interested in this distance from here to wherever the center of mass is, somewhere in between those, right? It will be, hold on one second, I'm just going to mute those announcements. I'm coming. All right, I'm back. Sorry. So if we treat that like the axis, then I'll get the distance from the axis to the center of mass. So that's not a bad choice. But there's lots of different ways you could do it. But you do have to decide where your 0 point is. So now the location of my first point, it's half the distance here, which is 0.2 times the mass, 0.1, plus this is 0.4 times 0.05. Right? That's 0.2 away from my 0, that's 0.4 away. And then when I do this, I should get 0.267 meters. That's the distance from the axis to the new center of mass. Why do I need to know that? Because that's what's changing height. So the last thing I need to do is say, okay, if this is the axis, and this is the center of mass, this is 0.267, that's the length of that, and it's going to rotate like this. The thing that changes height is the center of mass. So this is 0.267 here. That distance doesn't change. This distance here is 0.04 meters from here to here. And that means this distance here is 0.227. So the angle that we're looking for finally is the cosine inverse of adjacent over hypotenuse. And that is equal to, make sure that I am in degree mode, I am. So finally we have the cosine inverse of 0.227 divided by 0.267 is 31.8 degrees. And boy, is that a good problem there. If you did it in your notebook or wherever in less space than that, well, in less writing than that. I suppose if you write really small, you could do it in less space than that. But you can't do it with less writing than that. You can't. This is how much you have to write. That's the way it works. If you don't like that, I'm very sorry, but this is the way it is. You have to write all that stuff down. Have a nice day.